Hello, I am Emre Özdemir from Istanbul Technical University. Today I will be talking to you about UNR-2, a new chromium cyanide-based fluorescent probe we have developed for the detection of mercury cation in the near-infrared range. First, I will briefly touch upon a few topics related to this study, then I will provide information about the synthesis and characterization of UNR-2. After proving the structural integrity, I will move on to the work we conducted for mercury detection. Finally, I will discuss future plans and conclude with a short summary of the overall study. We chose to focus on the detection of mercury ion because in daily life it is used in equipment such as barometers, thermometers, batteries and dental fillings, and it has significant effects on both the environment and human health. Even very low levels can cause serious damage to various systems in the human body, especially the central nervous, endocrine and cardiovascular systems. Since it has a low toxic limit, monitoring its presence in the environment is critically important. Due to these effects, EPA has set a limit of 2 ppb for mercury in drinking water. Today, many methods are used for the detection of mercury. Some of these methods utilize instruments such as atomic absorption or atomic fluorescence spectrometers, as you can see on the screen. In this study, we preferred UV-vis absorption and fluorescence spectroscopy methods for the detection of mercury. The instruments used for these techniques are shown on the screen. So why did we choose these methods? These instruments have simple working principles and are easy to operate. They don't require long training times and analysis can be performed quickly. Moreover, since these instruments do not require additional equipment like cooling or flame generation, the analysis can be performed cost effectively. Recently, as smartphones have also been introduced as alternatives for scientific analysis for all kinds of chemical species detection. This approach, which is highly adaptable for further development, allows for rapid and accessible analysis for almost anyone. Its biggest advantage is its potential for field analysis. When properly developed, this method allows detection of a target species directly at the sample site, without the need for a laboratory environment. Of course, to work with these methods, one needs a selective probe for the target analyte. The probe must be both fluorescence active and colorimetric. In this study, the primary sensor platform we chose is the chromium cyanide dye, called ICS, shown on the screen. This platform was first synthesized by our group, and one of its biggest advantages is its ability to operate in the near IR range. This allows for more reliable analytical results and provides a suitable condition for working in cellular environments. Another feature of this platform is its ability to open and close its spironolactone ring, much like rhodamines. By utilizing this feature, we can develop various turn-on probes such as UNR-2. As shown in the scheme, UNR-2 was synthesized from this platform. The carboxylic acid form of ICS was first converted to its hydrazine form using hydrazine hydrate and BOP reagent. Then ICS-H reacted with phenyl isothiocyanate, yielding the target UNR-2 probe. To elucidate the structure, we used several characterization methods. We started with proton and carbon NMR spectroscopy, and the observed chemical shifts and integrations matched the proposed structure. These results were further supported by HRMS and FTIR analysis. In HRMS, we observed a peak representing the molecular ion with an additional proton, matching the calculated result. FTIR confirmed the presence of functional groups such as the amide carbonyl and secondary amine groups. These analyses were enough to confirm the structure. However, to better understand the molecule, we used 2D NMR techniques. Similar to seeing the crystal structure of the molecule, the goal was to elucidate the molecular structure thoroughly. We performed three different 2D NMR analyses in addition to APT NMR. The resulting spectra can be seen on the screen. As a result, we were able to confirm the chemical shift of each atom in the molecule with high precision as shown in the table. Another feature of UNR-2 is its molecular rearrangement upon interaction with mercury. At least, based on literature, we anticipated that the molecule would react as shown on the screen. We confirmed the formation of imidazole structure via HRMS, where the molecular ion of UNR2H was observed. The main peak precisely matched the molecular weight of NR2 after mercury sulfide was removed. The resulting structure lacks the spironolactone ring seen in NR2, yielding a green fluorescence in the presence of mercury. The detection mechanism is based on this reaction. Now let us move to sensor studies of NR2. After fully characterizing its structure, we started evaluating its performance as a sensor. The first step was identifying optimal working conditions. DMF HEPAS 321 was found to be the best environment for achieving maximum sensitivity and selectivity. Optimized conditions are as shown in the screen. As shown in the top graphs, the probe responded to mercury within as little as 10 seconds. The bottom graphs illustrate the working pH range for mercury detection, which was found to be between pH 3 and 9. Since we also aimed for cellular applications, we selected pH 7.4 as the working condition. After optimization, we performed selectivity and interference tests using both methods. These confirmed that the probe responded exclusively to mercury and was not influenced by other species. Following this, we conducted calibration studies for both methods. According to the literature titration results, the detection range was 0.033 to 5.63 micromolar for the mercury ion. The calculated LOD values were 0.11 nanomolars for UVVs and 0.18 nanomolar for fluorescence, both well below the acceptable limit for drinking water. We also performed a separate calibration using a smartphone. In this approach, the NR2 solution was placed in a cuvette and incremental amounts of mercury chloride were added. After each addition, a photo was taken under a fixed and well-lit setup. The captured images are shown here. The RGB values were then extracted digitally. As the solution color changed, the RGB values varied accordingly. We found that the G value had a linear relationship with the mercury concentration, allowing the detection of mercury in the range of 0.033 to 1.40 micromolar. To the best of our knowledge, these are the lowest levels detected using a smartphone-based method. We also tested these calibration ranges on real-world samples for mercury detection. Various water samples were contaminated with known amounts of mercury, and the recovery values, as shown in the table, demonstrate how accurately the method detected the spiking levels, yielding the results were very close to 100%. The same approach was applied using a smartphone for analysis, yielding results comparable to those from the other two methods. In the case of food samples, a semi-quantitative approach was used. Corn and rice were selected for this study. The samples were first immersed in the probe solution to allow ONERIKI to absorb. Then these food samples were added to solutions with known concentrations of mercury, and color changes were observed at varying intensities. This confirmed that the probe can effectively react with mercury within the food matrix. In addition to these studies, we have several future plans. First, we intend to utilize the near-IR properties of the probe for cellular imaging of mercury. Both healthy and cancer cells will be used to investigate the probe's behavior. The other two plans aim to expand its practical applications. One involves printing the probe onto paper using a printer, creating a pH paper-like sensor that operates based on color changes. The other involves integrating the probe into an Arduino-based sensor device for rapid and reliable field detection. To summarize, in this study, we successfully synthesized and developed NR2, a chromonilium cyanin-based near-IR probe for the detection of mercury. The sensor studies demonstrated that the probe operates across a broad pH range, is highly selective and sensitive for mercury, and can be used with UV-Vis, fluorescence, and smartphone-based methods. Its versatility makes it suitable for a variety of future applications. Finally, I would like to acknowledge and thank the Scientific and Technological Research Council of Turkey for supporting this work. That concludes my presentation. Thank you for listening.